Alrighty. So, hello everyone. My name is Neil Jackson, and this is the test wrapper for test number 1. Test 1 wrapper. I will be going over number 3 with a focus on 3B. I will review A really quickly. So, problem 3A, let's see here. So we were given that some sort of charge Q is placed at a positive distance A away from the origin, and that there's a constant electric field going in all directions of space, and that electric field, E sub C, is equal to negative E 0, 0. Alright? In part A, we were asked to determine the location in space where the net electric field is 0. Alright? So, there's only 2 electric fields at play here. There's the electric field caused by the malfunctioning lab equipment and the electric field caused by this positive charge Q. Alright, so pretty easy to set up. We want to find where is the electric field equal to 0. So the electric field of the positive charge plus the E of the constant charge should be equal to 0. That's the goal. By using some algebra and basic vector knowledge, we can wind up realizing that the magnitudes of these 2 fields must be equal, and that the directions of these 2 electric fields must be opposite. Equal in magnitude, opposite in direction. Kind of reminds you of reciprocity from Physics 1, right? Alright. Magnitude is easy enough to find out. We're just dealing with KQ over R squared. I'm using K for the electric constant. And that's just going to be equal to the square root of negative E squared. Now that's just the magnitude of E, and we're taking the square root of that, because it's magnitude, right? And our goal here is to find R, because this position R is what satisfies this equation up here, which is where the electric field is 0. So by using algebra, I'll let y'all derive this for yourself, but we wind up getting the magnitude of R is going to be KQ over the electric field referencing this E up here. And when we do the direction, we wind up, or the way we do this math is we just say that the sine, it's the sine of Q times R hat equal negative 100, and we're using negative 1 because that's the direction of the constant electric field. We wind up getting R hat is equal to a positive 1. Right? And then we wind up multiplying these 2 together and then flipping the sign, because when we multiply these 2 together, this will be the position, this will be the vector describing the location to the place of 0 field, but we want the position of 0 field to our observation location. So we need to flip the sign, and we wind up getting that distance to be A plus the square root of 1 over 4 pi epsilon naught Q over E, comma 0, 0. Alright, and this is our wonderful answer for 3A. 3B gets a little bit more trickier, because it's wanting us to say, okay, where do I place an electron, specifically a negative point charge, such that the electric field at the origin is equal to 0? Alright? We're using the same premise. We have 3 electric fields to work with in this problem. We have, we'll say E net should be equal to 0, which this 0 vector should be equal to the constant electric field by the lab equipment, the electric field from the positive charge, and the electric field from the newly placed negative point charge. All right. And obviously we want to find the position of the negative charge. So we want the R vector from this electric field. So using some algebra, the electric field of the negative charge should be negative EC minus KQ over positive distance, R hat of the positive. I just went ahead and expanded the electric field of the positive charge from the beginning because it just makes seeing the algebra maybe a little bit easier. All right. Then we can evaluate or break this down into magnitude times the direction, which will be the square root of E plus KQ over A squared to be squared times the unit vector 1 I hat. All right. We can then proceed to break this down into the magnitude of where negative R is, which is simply the square root of KQ over E plus KQ over A squared. And then the position, normally there in the normal R hat, there's a -1 right here. However, we're once again flipping the sign around because we want the position we don't want the position from the negative charge to the origin. We want the position from the origin to the negative charge. So we're just flipping the directionality of the vector. So then we wind up getting that our final solution will be root of KQ over E plus KQ over A squared. 0, 0. And that is our solution. Thank you very much for watching. Y'all have a great day.